Let's do a video on NMOS loaded logic. Um, and subtitle would be the, the pitfalls of the apprenticeship model, meaning not having strict prereqs on what we're doing, uh, just throwing people in the deep end a little too much. So here we have LTspice. We have 3 inverters and 3 symbols. If you right click, you can open up the symbol or the schematic. And here we have a resistively loaded NMOS transistor. You might see this still in the textbooks because it's an easy way to start talking about things. And if I right click on the NMOS, you'll see I've made some modifications where actually this should be length of the driver, and this should be width of the driver, and then the area of the source and drains and the perimeters are all set. So, and what we did is rather than put it to VDD and ground, we have these ports, the ports of the ports, so that for later on. So that's resistively loaded. Then we have diode connected, and here's a load transistor connected as a diode. Because when you plot ID versus VDS, it looks like a diode. You right click on that, you can see I have parameters of the length of the load, the width of the load, the area and drain parameters. So what we're doing is we're replacing a rather large transistor that would take up a lot of area with a transistor. You have a driver, and length, width, etc. There's advantages and disadvantages of everything, which it'll be just better to show simulation. And then we have a linearly connected bar where they're not shorted now. You can control this gate voltage independently, which can actually make the device work after fabrication if you get things wrong. So we should have length of load, width, and the area and perimeters. The area and perimeters are setting the parasitic capacitance values, which actually determine how fast you can go. And I'm just double checking my work here. Length of driver, width of driver. Okay. Now, just a quick thing. Yeah, in modern devices, this NMOS transistor is replaced with a PMOS transistor, and it has a lot of advantages. But you need 8 masks or 7 masks minimum to do it. So it can be hard to use as a research platform. Now, just as a quick aside, once you get your process done, you can use a place like Skywater with your, you have your one process step that works. They'll take a wafer out of their commercial line, give it to you for your special processing, and give it back. And so then you can have 130 nanometer devices, PMOS, NMOS, MEM resistors, and 5 letters of metal. This really is beyond what can be easily done at a university. So we stick to the 4 masks. Sometimes we even do 2. So just want to make sure I save this file. And so now what I'm going to do is a DC sweep. So VN is going to go from 0 to 5. So just some things to call out. This is V in versus V out, and the slope is 1. Right? So the output is not only being inverted, but it's being amplified, trying to amplify it to where it clips at the rail. So now we can start to see some differences in the devices. So we have purple and gray, right? They start at 5 volts, and excuse me, you can see they're trending towards 0. Although the purple and gray, which is the diode connected MOSFET and the linear connected MOSFET, aren't exactly going all the way to 0. So their output low might not go low enough, where this one, right, it starts at 5 and it goes to low, and that's the resistively loaded one. Well, the thing is you can see, I have a low voltage and it's making it high. I have a high voltage making it low. And yes, we have this transition region. How do you know if it's really an inverter? Well, you take the derivative of these, and do they go through -1 twice? Because if they do, that means any signal in here will be driven to 5 volts, and any signal over here will be driven to low. But yeah, there is a gain in this transition region. And as a quick aside, you can use that for analog with a whole lot of work, right? But you've got to get these output highs and lows first. And so notice we have purple and we have the gray. I'll come back here and tell you what those are. So the resistively loaded one, when this transistor is off, there's no current flow, no voltage drop, and V out equals VDD. Great. But the linear one, oh no, let me come to here. Diode connected one, however, yes, no current should flow, but in order to V out to be VDD, current had to flow, which means there needed to be at least threshold voltage across this to charge that up. So it means it can't really go to VDD. And we see that. Instead of 5 volts, it's like 3 and change. And you might say, if you were clever, you looked at the spice deck and said, hey, VT was half a volt. What's going on? I'll tell you, is that the source is not the same as the body, and the gamma is rather large, and so the threshold voltage drop here is significant. Right? So, yeah, what your guys' project is to come up with a spice deck so that we can come up with the voltages and widths and lengths to get things to work before we actually commit to a process. These numbers here were just pulled off the web somewhere. You guys have calculated KPs and VTs and all of that. Now then, something else I want to point out is here's where I define the width and the length and areas and drains. And so, yeah, there's the depth of drain. So everything is programmed right here. So once you fix it here, it's fixed everywhere, right? But I will show you a bit of a trick. So I'm looking at, so the resistively loaded one, right? It's pretty sharp and it's going a lot lower than the other two, which it's inverting, but it might not be low enough to drive the next gate. So what I want to do is come back here, and I'm thinking the driver needs more power, right? So what I'm going to do is I'm going to increase the number of parallel devices to 4. I guess I'd had it set to 2. Ready. And so now should be able to rerun, and it got below 0.5, it became better, right? But it's just becoming kind of hard to get that to go low. And right now, again, we're just kind of being intuitive. Oh, there's another reason why it's not quite working, is that the transistor length of the load needs to be big. Like we'll have to explain this later, but um, the length, because we want it to be like the higher the resistance, the better. Want to, when I increase the length, the resistance of the transistor goes up, and I had set that to 10. It should have been. So actually, we should get some good depth. Now we're getting somewhere. Okay. So now the other devices are going, well, very close to zero. So then I should come back here. So I don't really need 4, probably 1 will cover it. Let me double check the diode connected. That one's set to 1. Okay, so the linear one actually isn't going as low because in the linear mode, you're not getting as much current flow for the voltage. So that one could use a multiplier. So let's put that to 2. Now, it's working fairly well. But this is what I mean, is that the circuit designer controls the width and the length and the connectance. Now, the still the diode connected one only goes to up to 3.75, where the other two are going from 5 to 0. So the thing is it's not enough just to be able to have one logic gate. Logic gates drive logic gates. So you want a strong 0 so that the device will go high, and you want a strong high so the device will go back to 0. Now, one way to test that is through the Ring Oscillator. I'm just going to use this. Actually, we'll use this one. Okay. Now, in practicality, 3 uh, 3 stages of a ring oscillator are not enough. It might not really oscillate, and if it did, it'd be so fast that you wouldn't be able to measure it, and you're not really measuring the device. Be so fast, you'd be measuring what would be keeping things slow or affecting the speed is all the parasitic capacitors in the device. So let's give it a net name. So it doesn't really matter. Then we can make an initial condition dot C equals 0. And then we want transient. Now we really don't need 5,000. Really, probably a microsecond, as long as it needs to be. So now, hopefully this should oscillate. Okay. Something's happening. Oh, not really. Wait. Just want to get rid of this. So in fact, it's not going rail to rail, but it is oscillating, right? And if I want to just measure the frequency very easily, just do the FFT and well, what do we got? 31 megahertz, okay, which is pretty slow, but that this is a device where the drain and the sources are rather large. So we and the XJ is rather large. Um, so we're going to see that. Now, let's just see what. So that was diode connected. Let's have that extra gate voltage, which allows rail-to-rail operation. So quick simulation. So I might have made a mistake with connecting that the right way. Oh, yep, the grounds are a little bit different. Well, so now you know what it looks like when ground isn't connected. Let's just it's about the same. And you could do that for the other one. Now these don't go rail to rail, but it does mean that the logic levels will work. If I wanted more rail to rail, I would bring this out to an oscilloscope. I would take inverters and use them as amplifiers to amplify the signal. But once you have a spice deck, yeah, you have three different ways of making an NMOS inverter, right? You get your widths and your lengths right and go from there. Now, could explore, right, like a length of 100. Well, that is taking area, right? 10 didn't seem, we had 10. I didn't really like it that much, but, would 10 work? 10 does work. In fact, it's even faster. Yeah. Let me make sure I did Okay. So, so the reason why it got faster, we just do here, is that we made the resistance of this lower so that when this turns off and we're charging high, the RC time constant is lower, so it charges up faster. So if I was trying to make a faster device, yeah, a length of 10. But if you recall, I wanted better logic values. So I might say, well, I want to have a trade-off between logic level and speed. So I have to go do undo. I might have had some things reversed. No, could be. So I'll go 50, right? No. So instead of 100, I'll do 50. So the logic levels should be better, but it, you know, should be slower. Yeah. So you can see there's like a trade-off. Now we should have hand calculations for that. That I should say are conflicting. Conflicting requirements. And so, you know, you would use LTspice to verify that you can, that things will still work even, you can't hit every spec, but you might be, you have to change your spec to a speed of, less than this is okay. You know, a speed, as long as the speed is faster than this, and the logic level low is lower than this, logic level high is higher than that, right? Rather than equal to any particular thing, it'll work. But good thing about the is that the linear load, even though it, excuse me, takes another pin, it's that you can adjust the logic level high with it after the fact. You get away from that threshold voltage drop. So hopefully, right, you can see you set everything here, you set it in the devices, but now that I have symbols, I can make higher level things. Just like in normal LTspice when you're using op amps and things like that, right? You don't see each transistor. Okay. But even still, you could say, oh, well, what if I only had 6 volts here? It seems to oscillate. No, not really. Oh no, I have. Yeah, it's still working. Slower, but or maybe not. Yeah, slower because it doesn't have enough drive. But if ultimately it can't work, right, because the threshold voltage in gamma is too high or Kp is too low, right, well, then you have to go back to the process deck, come up with a better spice model. Okay? But a lot of times, the process person, they're coming up with the latest process. They extract a spice deck, and the circuit designer just has to take it and then be clever with getting things to meet power and timing and logic level. Okay. But again, we're using NMOS loaded logic, not CMOS. Um, it's an older technology, but it's a much easier thing to do research on various layers. Right? Anyway, that should be it.